Okay, so I want to start discussing how to solve quadratic equations, a concept that you guys should have a good amount of familiarity with. However, the extent in which we discuss these questions will be maybe a little bit deeper than what you've done in the past. In addition, the reason this is coming early on in the course is how much factoring, or is due to how much factoring is conducted throughout the entire course. Okay, it will be one of our main procedures as we move through. So I want to make sure that we all have a good understanding of what we're doing analytically, what we're doing by hand. Okay, with the actual procedures. I want you to, we don't get into it too much today, we will tomorrow or the next day, in regards to why you do those things by hand. Why do I take two numbers and multiply them together and then see if they add together, multiply together to give me my C term and add together to give me my B term when I have a quadratic equation? Why do we do that? Why does that technique work, or that shortcut work? Why does the quadratic formula work? What's that all about? So those are things that we'll investigate and we'll talk about as we move through the course or the next couple of days. But like I said, these techniques will be used all the time throughout this course. You get to calculus, guys, and there might be 10 questions in homework, and intermediate processes for those 10 questions might incorporate. Each one of those questions might incorporate a different factoring style or factoring technique that, at that level, it's just going to be assumed that you know them, okay? It's kind of like at this level, if I give you two numbers and ask you to multiply them together, you can do it, right? Because you've been doing it since 3rd grade. So when you get to calculus, you've been doing factoring since the 9th grade or 8th grade, some of us, okay? So the thought is that at that point, those are intermediate processes that should be mastered. And then that's kind of the goal in this course. If you think about Algebra 2, there's a big section of that where you just focused on factoring, right? Okay. There was a purpose for that. All right. I think this is section 1.4. Early on, we're going to kind of hit and miss sections in chapter 1. There's not a lot of stuff in there. I think there's like 10 total sections, but we only hit maybe 4 or 5 of them. Okay, so I think this is 1.4. We skipped 1.3. Okay, so quadratic equation. A quadratic equation is of the form ax squared plus bx plus c equals 0, where A, what? Yeah. B and C are real numbers. Ax squared plus bx plus c equals 0, where A, B, and C are elements of your real numbers. Meaning your coefficients here and your constant, C as you consider your constant, those coefficients or constants can be anything that they want to, as long as they don't have an imaginary component. That make sense? That's what we're focused on for the next couple of days, is being able to factor those types of things. Now, here is the thing. Down the road, we will allow A, B, and C to have imaginary components. And the way that we target those, the way we factor a quadratic or an expression that is of quadratic form that incorporates imaginary numbers, it will be the exact same techniques that we learn here. Okay, it's a little bit messier, it's a little bit more detailed in the process because you got a lot more terms because of the A plus BI aspect of things. But what you learn here, we will reuse later on. There are some techniques here that we learn within the next couple of days that when we come across trigonometric equations and trigonometry, I'll ask you to remember back to the 3rd or 4th day of class, and we were actually factoring stuff, and we did this process. Okay, I'll say, well, that's what we got to do now, and it'll be April when that comes up. Okay, So there's a lot of stuff right now that we're going to be learning that is going to carry over. Thank you. Okay. All right. So when we factor, guys, there's going to be several methods for solving a quadratic equation. Obviously, so all of these techniques are going to solve the equation. Factoring, there is a, a lot of us kind of think that, these techniques are all considered factoring, and I'm kind of that thought process that completing the square is a factoring process. We're ultimately trying to figure out what numbers multiply together to give me something, okay? Which, when we talk about products, the things that multiply together to give me a product are factors, okay? But when we say number one here, factoring, we're talking like the product and sum technique. Two numbers that multiply together give me the C term and have to give me the B term. Or we're talking the AC method, which we'll see an example of today. Talking about GCFs, that kind of thing. Okay, so we have factoring. We have the square root property. I want to talk about some of these things when they're applicable, when you can use them. The square root property can only be used when your B term equals 0. Your B coefficient is 0. So essentially saying that you don't have an X term, right? Or a BX term. And then you can use the square root method. Completing the square. Okay. That is basically the technique that everything else is based off of. So I'm just going to say process or technique. Okay, so completing the square is kind of the all-encompassing process that will always work for solving a quadratic equation, except for the fact that it's a pain in the butt. It's a long technique. We have done some algebra to show eventually with some theorems and proofs that though that will work all the time, there are some shortcuts. Okay. So that's going to be one of the longer things that we do. You guys completed the square last year. We actually completed square a couple times in geometry when we worked with circles. And quadratic formula. Okay, this is the same as, I'm just going to say number 3 for completing the square. It's the same as completing a square, but it circumvents all the steps, say yes. What? Goes around. Okay, to circumvent something means to go around something. So it allows us to avoid essentially all the steps in number 3. Okay? You might even want to write down that the quadratic formula is your kind of maybe default procedure. Meaning, if I can't figure out to use 1, 2, or 3, use number 4, and it will always work. That being said, though, one of our goals in mathematics is to be efficient, right? Okay, especially if we're thinking ACT, 60 questions, 60 minutes. I don't want to be working on a factoring problem that I'm using the quadratic formula, chewing up 3, 4, 5 minutes on a problem where I could have used a technique out of number 1 there, out of the factoring techniques, and it took 30 seconds. Okay, so we want to be cognizant of the approaches, cognizant of the time that each of those approaches takes, and then apply the appropriate one when necessary. Okay? All right. let's talk about how many solutions quadratics can have. So when we talk about these solutions, guys, we're then going to, I want to graph the images that these solutions come from, or the way we interpret these solutions. So the first one is with a quadratic equation. When we graph it, okay, so there's my x and y axes. If I have something that's of the form ax squared plus bx plus c equals 0. Now, we talk about this with linear equations. This side here, this side of stuff, that's kind of the worst highlighter. Oh, I didn't even choose the highlighter. That side is going to be bear with me, everything froze back here. There we go. That there is a y equals. Does that make sense? That's going to be a graph. Okay? The other side, the 0, is also going to be a y equals. Okay? Well, what's y equals 0? What does that represent, or what, in my graph, y equals 0 is the what? Okay, it's the horizontal axis, so it's the x-axis, right? Okay, so when we talk about solving this type of equation, and we're talking about the solutions, what we're really talking about here, guys, is how many times does our graph cross that line y equals 0, okay, or your x-axis. So with quadratics, you've got some options. The first option is that your parabola does not cross the x-axis, or y equals 0, okay? So if it doesn't cross, that means there are no real solutions. Okay. However, two non-reals will exist. So analytically, when we do it by hand, we go through the procedures, we will get two answers that have I in them. Does that make sense? Be maybe like 2 plus 3I or something like that, or 2 plus or minus I radical 3. You'll have answers that show up like that, and you've seen those in the past, okay? But the graphical approach means then that you never cross the x-axis, okay? The second situation is when we have our parabola do something like this. It's a terrible parabola. Okay, so I tried to draw it so it touched. It's going to touch your x-axis one time and one time only. Do you remember the word from geometry that we would use to say touches one time and one time only? T? Nope. You didn't like them in geometry. Numbers. Not numbers. Sine, cosine, and tangent. Okay? So tangent is the word that we use for that parabola. We said that the parabola is tangent to the x-axis. Okay? So what this means is that we will have one real solution, but it'll be what we call a double root. You vaguely remember using that phrase in Algebra 2, double root? Ladies, do we remember hearing double root? No,
exactly.
I heard a yeah.
Who said yeah?
Okay. So a double root, what that means is when we solve our quadratic equation, you know that you guys have solved quadratics before, and you got like x equals 2 for one factor, and you got x equals 2 for the other factor, right? Well, the only answer is 2, right? But it showed up how many times? Twice, hence the word double, okay? Root is just a synonym, the way we're going to approach it, it's a synonym for x-intercept or a 0 or obviously then root. So those three words, root, 0, x-intercept, we're going to consider for all intents and purposes as synonyms. There are particular instances where maybe we want to use the word root instead of x-intercept or something like that, and we'll talk about those later on. And the last situation will be intersecting how many times? Twice. And these are the most common. Okay, so we get a solution there, and we get a solution from there. Okay, so we get two real solutions. We'll talk about this in more detail towards the end of this section when we start using the quadratic formula a little bit more. But there is part of the quadratic formula, which is, I'll just write it right here. It's that portion, the b squared minus 4ac, the thing that goes underneath the root symbol. Anybody remember what that's called?
Discontinuity. Discriminant.
Okay. It is the discriminant. Okay. My hope is, even early on here in the last couple of days, you're seeing a lot of vocabulary that is carried over from geometry, carried over from Algebra 2 and Algebra 1, right? We're going to use that vocabulary. We're going to know that vocabulary because when we see homework questions, we see test questions, that kind of stuff, it's going to use that vocabulary. If I don't know what those vocabulary words are, obviously I'm going to struggle with the directions, okay? So the discriminant, what it means to discriminate is just to recognize differences, right? Okay? Okay, so discriminate is not a bad term, okay? All it means is that you're making an obvious difference, or you're recognizing an obvious difference. So with the discriminant inside quadratic equations, b squared minus 4ac is the thing that allows us to make that difference. If b, or make that recognition of a difference. b squared minus 4ac, if that thing is less than 0. Think about this. If what is underneath the radical is less than 0, then you've got the square root of a negative, right? And the square root of a negative incorporates I, correct? Okay, we got to bring in the imaginary numbers. And that identifies to us that we have no real solutions. Okay? So that's what allows us to discriminate between having no solutions, one solution, or two solutions. Okay? If my discriminant here is equal to 0, b squared minus 4ac is equal to 0. That means I have one real solution, and it automatically tells me that that real solution is a double root. What that basically says, if you guys remember what we do with the quadratic formula, we have the opposite of b plus or minus my discriminant, right, all over 2a. Well, if this is 0, isn't the square root of 0, 0? So doesn't that just turn into negative b plus or minus 0 over 2a, which is just one amount? Does that kind of make sense? Okay. So my discriminant there, when it's equal to 0, tells me I have one real solution.
Bless you.
And what does my discriminant have to be if I'm going to have two real solutions? Greater than 0. It's got to be a positive number. So a negative discriminant, no real solutions. A 0 discriminant, one solution. A positive discriminant, two solutions. Is that okay?
Yes, sir.
Now, you also talked last year in regards to like y-intercepts when we graph these things. That y-intercept, that y-intercept, that y-intercept. Does anybody know the kind of the generic ordered pair for any y-intercept on a quadratic? What would be the x value of all those red dots I put in those three graphs? Yeah. The x value would be 0. Okay? So if I put x in for 0, or 0 in for x, wouldn't that go away? Wouldn't that go away? What's the only thing you're left with?
C.
So every one of these y-intercepts is located at 0, C. Okay? Now I'm running out of room here, but every parabola has an axis of what? Symmetry. And the axis of symmetry on every single parabola goes through the what? Not the y-axis. It might be the y-axis sometimes. What is, so the axis of symmetry is going to be the place where I fold, where maybe this graph here, the left-hand branch of it lands on the right hand, right? So that, I know yellow is not a good color here to choose. If I look at that yellow line, what is that point right there? The vertex, okay? Now, what you learned last year, hopefully, is that not only is that vertex going to be on the axis of symmetry, but that distance right there and that distance right there, the distance between an x-intercept and your axis of symmetry should be the same. Does that make sense?
Yep.
So your vertex is always halfway in between your two x-intercepts, your two zeros, your two roots. So as we work through these, guys, I know that when you were in Algebra 2, okay, because I know the standards, I was taught by the same exact teacher you guys were taught by, okay? When you work with these equations in that class, I know you did like one thing. You only focused on maybe graphing it. Or maybe you only focused on solving it algebraically or analytically by hand, okay? When we do it, a lot of times, we're going to do all those things, okay? We want to gain a greater depth of knowledge for these equations, okay? In regards to this process, we're going to have to use one real key idea, okay? Let me put something down to kind of prove a point here. If I write something like x plus 2 times x minus 3 equals, let's just say, let's go 12, okay? When I factor this, can I write this as x plus 2 equals 12 and x minus 3 equals 12 and solve those individually? Think about this. Think about this. I'm multiplying two numbers together to get 12, right? Doesn't that mean that number there could be 3 and that one could be 4? Doesn't it mean that one could have been 2 and that one be 6? Doesn't it mean that one could be 1 and that one could be 12? And doesn't it mean that maybe that one could be 1/4 and that one be 48? Does that kind of make sense? So there's a lot. If I have two numbers multiplied together equals something like 12, there's actually an infinite set of factors that I could come up with that multiply together to give me 12, right? So that's an issue. That is a huge problem for our process. What do we want that 12 to be? We want it to be 0. Because think about this. If I have x plus 2 and x minus 3 is equal to 0, that's a number times a number is equal to 0. that number might be anything, right? But if that number is anything, then doesn't that dictate the other number having to be 0? So that's a nice thing, okay? And that idea, that concept is the zero factor property. A lot of times I will refer to it as the zero product property, but what it says is if A and B are real numbers, and A times B equals 0, then A equals 0 or B equals 0. And that's the zero product or zero factor property that we use on the last step of every single quadratic equation that we try to solve. Okay? It would be nice in mathematics to understand it a little bit better, I think, to be able to have phrases in our textbook or in our notes that say, oh, well, when I multiply two numbers together and my product is 0, then one or both those numbers have to be 0 themselves, right? If that was the phrase written out in our book, I think people would understand mathematics a lot better. However, I can't use that phrase in a proof of something else later on, because there's no algebra to it. Does that make sense? This phrase I can. The A times B equals 0, that is giving me algebra that I can use later on. And we will use this factor property later on in an algebraic proof. Okay, that is one thing that I like to add to this course to get you guys to understand that the algebra that we've been doing, the algebra that we do for the most part in this class, really isn't the algebra that we do when we get to college. Okay? We like to do a little bit more abstract algebra when we get to college and try to understand the system of mathematics a little better that way. So we'll see some of those theorems later on. But the zero factor property just basically says you're multiplying two numbers together and you get 0, one or both of them have to be 0. Okay? All right, the last thing before we get into some examples. When we start factoring things, there is a hierarchy of ideas or processes that you want to go through that will make the process much more efficient for you. Okay? So the first thing I always want to be aware of or try to see if it exists is a GCF. Okay? Greatest common factor. Okay? I always want to make sure that, you know, if my quadratic equation is like 2x squared plus 6x plus 12, each one of those had a factor of 2 in it, right? I want to factor that out. I want to get rid of that 2 because it will make my next steps easier. If I can always work with smaller numbers than what they start me with, that's going to make things easier, right? So that's the idea. I always want to look for GCS, okay? The next thing is to use the product sum technique, which refers to two numbers that multiply to give me C, but add to give me B. Okay? And that's the one we can only use when the A coefficient is 1. Okay? If the product sum technique doesn't work, the next thing we're going to go to is the AC method, which we'll see an example. This is an example here of the AC method. Notice that there is no GCF in example 2. So if there's no GCF, I can't make that A coefficient, the 5, I can't make that a 1. Therefore, I've got to go to the AC method. If you remember, it's taking the 5 times the negative 2, getting that product and working through what that is. Okay? If that does not work, you're going to default to the quadratic formula, okay? Which is completing the square if you want to complete the square. But quadratic formula is just quicker. It's a quicker version of completing the square. Eventually, now I'll put like an asterisk here. Eventually, when we get expressions or equations that have multiple terms, more terms than 3, so 4 terms, 5 terms, that kind of thing, we might try a factor by grouping, which is really what the AC method generates for us, is a factor by grouping technique. Or we'll have to use the rational root theorem, which you guys remember from last year. That was the stuff that you use P over Q. And there's that stuff in red there. There's a whole chapter kind of dedicated to that. We might want to put in here, and I skipped it, but it's pretty rare to actually see it. But you might be able to use the square root method. And as before, we said that's when the b value was equal to 0. Okay. But I think when you see that'll be just something that jumps off the page, so you know automatically what to do. That's kind of the hierarchy that we want to go through. That should save you time in factoring. My hopes are that we don't always just jump to the quadratic formula, because in doing that you might waste 3-4 minutes, where if the square root method was available, or just the proc sum technique was available, you might be able to do the question in 30 seconds. Okay. That's kind of as we work through math and as you get deeper into it, you start to realize that one of the main goals that mathematicians have is not just to be able to come to a solution or make an argument about something, but to do it as concisely and as efficient as possible. Okay, that's kind of the game that mathematicians play. Okay, so with this idea in mind, when I factor, every time you factor, you need equal to 0, right? In my mind, whenever I see x squared or x cubed or x to the 4th in an equation, I see this thing right here. That just, it's in my mind's eye or whatever, and I know that I have to use that so that I can get a, come on, I have to use that idea so that I can then address the use of one of these tools over here. Okay? So when I have x squared plus 5x equals 24, I have to do all my work to make that 24 get to the other side. So this is obviously, hopefully, a pretty simple question, right?
Yep.
Okay? So what do I need to do there? What am I looking for? This technique, isn't it? Proc sum technique of two numbers that multiply together give me negative 24 and have to give me 5. What are those two numbers? Doesn't the 8 have to be the positive one? Okay. And a lot of people then will jump straight to x being 3 or x being negative 8. Does anybody do it that way? You just jump straight to it? But remember, why we can do that is because we've got a number multiplied by a number, and it's giving me 0. That means this number here must be 0 or that one. So right here, this stage right there is the 0 product property. which is allowing me then to get x to be 3 or x to be negative 8. Okay? Where if that wasn't a 0 over there, I can't do that. Okay? Because there's an infinite number of, if that was a 12 or like we did that earlier, well, x minus 3 might equal 4 and x plus 8 might equal 3 then. Or it could be 2 and 6. And I just I can't narrow it down like I can if it's 0. Is that okay? All right. If we were to, we'll just do this real quick here. Let's erase this. I don't have a good way to erase everything at once with this new stuff. All right, let's go. Let's say if we want to graph this. That and that, tell me where I cross the what? X-axis. So 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, right? Okay. Where did you tell me the vertex was located? Say, okay, 0C, 0 comma C is not the vertex, that's the y-intercept. Okay? So 0, negative 24 is going to be my y-intercept. Does that make sense, everybody? Okay. Now my vertex is going to be where in relationship to my x-intercepts? Or where in relation to 3 and negative 8? Right in the middle. Okay? So what's the distance between 3 and negative 8? I'm standing at 3 and I need to walk to negative 8. How far do I walk? Walk 11 units, don't I? What's halfway of 11 units? 5.5. Meaning that from either this point moving that direction or this point moving that direction, if I go 5.5 units to either direction, I should be at the middle, right? Okay, so I'm going to move, so there would be 3, there would be 4, 5.5 would be right there. Does that make sense? So my vertex, so that x value right there is negative 2.5. Does anybody know how I find the y value of the vertex? It has to do with this thing right here. Do you know an x value? Can you plug that x value in right there? Can you plug it in right there? And what's it going to spit back to you? Let's spit back to your y value. And I believe, last class we actually grabbed our count. I think it's negative 30.25. Yeah. Okay. So negative 30.25 will be my y value. So now when I graph this thing, coming down through here, there's my vertex. I'll come up through there, hit that one, and go through. So that vertex right there is at negative 2.5, comma negative 30.25. Okay? And now our ability to do that is going to be essential for some of the story problems that we're going to see later on in this section. Okay? Now that's concave. You guys remember the word that we used for that one? Concave. Is that up or down? That one is concave up. Okay? If you can fill it with water and the water doesn't fall out, it's concave up. Okay? Concavity refers to kind of the impression or the dent or whatever inside our curve. Does that make sense? Okay? And that dent here is kind of pushing up. Does that make sense? Okay? So we call that concave up. All right, let's do this bottom one, and then we'll be done.
Yay.
All right, so it's already equal to 0, right?
Yep.
Okay, so is there a GCF?
No.
Can't use GCF. Is there can we use a square root method?
No.
No. Can we use the product sum technique?
No.
No. Once this value here, once you recognize that there's not a GCF, that value cannot be turned into 1, right? The product sum technique can only be used when that's a 1. So then we have to use the AC method. Okay, so the AC method says take A times C, which in our case would be 5 times -2, and that gives you -10, right? Now I'm looking for two numbers that multiply together to give me -10, but add to give me that number right there. -10 and 1. Okay? So then, what you do is you rewrite this equation the exact same way, except you're going to expand that using those two. Meaning I write it this way. You guys remember doing that? Okay. Now, there's an infinite number of ways to rewrite -9 as a sum of two values. But there is one and only one way to do it so that we can introduce factor by grouping. And that's kind of what we're doing here. We're trying to develop 4 terms so we can factor by grouping. Now, it does not matter how you put these two things in here. Put them as -10 and then +1, or if you want to go 1 and then -10. It doesn't matter. But the next thing you're going to do is you're going to grab those first two. Okay. Now, is this 5 positive? Okay, so I actually, inside that first set of brackets, I incorporate the sign of the first term. So when I group the back two, it's the same principle. I'm going to grab the sign of that 1x. Okay, I know at times, and maybe even in some textbooks, you don't see it written that way, where they leave that positive symbol, that plus sign, outside, and it gets people confused. If you incorporate it, and I think it makes the process a whole lot easier. Now we look at these two things a second. What do they have in common? What's the GCF in that set of brackets? 5x. And what would be left over on the inside when I factor 5x out? X minus 2. Okay? Now, what's the greatest factor that can come out of those two? 1. And it leaves me x minus 2. You guys remember the goal of this stuff was to show that that thing there and that thing there end up being the same, right? If those end up being the same, then factor by the AC method works. And what we end up doing is we write 5x plus 1. So it's these essentially factors of the individual components. They become an individual factor. And what's my other factor? X minus 2. If I was uncertain about whether this was correct, could I FOIL that and see if I get back to what I started with? Yep. Yeah. So then zero product property tells me this. And then algebra tells me that. And those would be our two solutions then, right? You guys remember those two techniques? Yeah. Okay. Example 3 is very similar, except for there's some preliminary work I've got to do. I've got to distribute that 5 through, right? And then move all those products to the left-hand side, and then I can start through the factoring process, okay? You need to make sure that when you do these problems that you do all implied algebra first, get your equations equal to 0, and then you can start the factoring procedures. Okay? You dropped something.
Got him.
There is an assignment on WebSign. It's not due till Monday. You probably can't do all the questions. Actually, I know you can't do all the questions because there is some new stuff in this section that we'll talk about in regards to some story problems. Okay? But you can start that, maybe do 5 or 6 of them, and then that obviously make the work on you tomorrow a little bit easier.